Hi guys, my name is Gene Doyle and I plan on teaching chemistry. Unfortunately, I couldn't make it to our first micro-teaching session, but I had spoken with Dr. Mahar over the phone, and I think I have a better understanding now of the I do, you do teaching model that you guys went over. So I had all my lesson plans typed out and ready to give to you, but it's a little hard to show in this format. But the unit I plan this lesson around is bonding, and specifically intramolecular bonding. I know a lot of you took chemistry a long time ago, so you're probably not familiar with these terms. But what I would plan to do with my class is go over what they had previously learned in the last lesson about what bonding is and the three different types of bonds in chemistry. So just to briefly review, I kind of prepared a synopsis here of the three different types of bonding. So first is ionic bonds, and that is the result of the transfer of electrons from one atom to a more electronegative atom. And one example of an ionic compound is salt, table salt, sodium chloride. And I should mention that ionic bonds are composed of a metal and a non-metal. In this case, the metal is sodium and the non-metal is chloride. And then we have covalent bonds, which is composed of sharing of electrons between atoms and between specifically non-metals. One example of a covalent compound is sugar, made of carbon, hydrogen, and oxygen. It's an organic compound, and it's a covalent compound. And then lastly, we have metallic bonding, which occur in all metals, so copper, nickel, iron. And metallic bonding is unique in that it allows for a delocalized system of electrons to freely move in between the positively charged metal cations. So in this case, copper 2+, and electrons are arranged in a rigid pattern, but these electrons are actually able to flow between copper atom to copper atom. So the property of these three different bonds that is important for the lesson that I planned is conductivity. So conductivity is basically allows for the flow of heat, the flow of electricity, and there's a specific property that allows for conductivity, and that is the movement of charged particles. So ionic substances in their solid state do not allow for the conductivity of electricity. Neither does sugar, but metals, on the other hand, and this is why we use metal frying pans to cook with, because they are good conductors of electricity and heat. And that is because these electrons are free to move around, so they're able to move, which allows for current to be passed through them. Okay, so that's why metals are so unique. Ionic compounds in their solid structure do not allow for the conductivity of electricity. But in their aqueous form, when you dissolve them in water, when you dissolve salt in water, they actually dissociate, these molecules dissociate into individual ions, sodium ions and chloride ions, and these ions are charged. So when they are in their aqueous state, ionic compounds dissolved in water, they actually allow for the conductivity of electricity, but not in their solid state. Covalent structures, compounds on the other hand, do not allow for the conductivity of electricity in their solid state, and when you dissolve them in water, they do not dissociate into ions. They do not dissociate into electrolytes, which is another word for ions. So they stay neutral, and they do not allow for the conductivity of electricity. So to summarize, metals in their solid state are great conductors of electricity because their electrons are free to move. Ionic compounds only conduct electricity in their aqueous state when dissolved in water, and covalent compounds never can conduct electricity. So I know that was a mouthful, but it's relevant to the task that I'll be having my students do. And in my teaching and learning science class, we are learning all about teaching through science inquiry, which in summary is student-centered, not teacher-centered. It involves active engagement of students, so actually hands-on learning. And it involves a collaborative effort, so students working together to actually develop, plan, and carry out investigations and experiments to test their hypotheses that they create. So this is in comparison to traditional science learning where you're just taught concepts, you're taught facts, you're given procedures to follow in a stepwise manner, and it really doesn't really facilitate substantive discussion between students. So I'm trying to plan lessons that are inquiry based. So I'll read you this from my task sheet that I made. But the task that I'll have my students do is they will be given 3 solid substances of unknown identity, labeled A, B, and C. One will be covalent, one will be ionic, and one will be metallic. So their job will be to work in a group to develop a procedure, so they actually have to develop the procedure, to identify which solid is composed of each type of bonding based on the known properties of each. So I gave them a hint, so what property of a substance allows for the conductivity of electricity. So they know they'll be dealing with that property. And I say here that they'll have to defend why they did what they did and how they were able to identify the substance of each. So this really should make them think critically about how to develop a procedure to identify the unknown solids, right? So over here I have, and I took this from the chemistry classroom in the school I'm working in, but I have simple conductivity meters. So this is just a battery. It has 2 prongs here, one positive and one negative electrode, so an anode and a cathode. And when this is on, and you stick these 2 prongs in a solution or onto a solid, if that substance conducts electricity, these lights will light up. If the red light lights up, it's basically low conductivity. If the red lights up pretty bright, it's about medium conductivity. And if both lights, the green and red lights up, that means it's a great conductor of electricity. So, and then I have what would be in test tubes labeled A, B, and C for them. Sugar, salt, and I didn't really have access to any ground up metal. I would if I was actually teaching. But for the purposes of our experiment here, I just used a copper penny as the metal. So that would be the setup for them. And trying to incorporate the I do, you do model for our purposes, what I would do is I would have 2 beakers here, and I would show them the conductivity meter like I did just now and tell them how it works. And I would say, okay, one of these beakers I'm going to go fill with tap water from the sink, right? So regular tap water. And then here, I was actually able to find distilled water. Well, my mom was able to find it in ShopRite. Didn't think we'd be able to buy any water during, the virus crisis, but we did. So distilled water is water that is boiled, evaporated, right, distilled, and the steam is condensed and collected. So what that does is it leaves all the dissolved materials, any salts or minerals present, any dissolved ions, in the pan, wherever they're evaporating from, and the water that they collect is pure water. So no dissolved ion species, no charged particles, pure H2O in this beaker. Whereas the tap water, as most of you probably know, has dissolved substances, right? Chloride ions, fluoride ions, sulfide possibly, any minerals present, and they're charged species. So remember what we just talked about with conductivity. If there are charged particles in solution, it allows for the conductivity of electricity. So what I would show my students is how you take this conductivity meter, you have to turn it on, it's just a simple switch. And first I would place it in the tap water. And I might have to come closer to the camera. But when I do this, you should see that the red light lights up. Barely, but it's lighting up, which means, I hope you can see that in the camera, it's actually conducting electricity. The green light's not lighting up at all, but it is conducting electricity, which means there are charged particles in that solution. Now, I'll wipe the prongs off. That's in comparison. Now this is pure distilled water, no dissolved species. And we get no light, nothing lighting up, right? So pure water actually does not conduct electricity. So if you were in a bathtub with distilled water and you stuck a hairdryer in there and it was pure H2O, you wouldn't get electrocuted. But if it was tap water and any dissolved species, and it doesn't take much, it would be able to conduct electricity. So knowing everything they do now about the properties of the three different types of bonds, how to use the conductivity meter, which I demonstrated to them, and I don't want to give away too much, but I think with everything I gave them, they should be able to recognize that a metal will conduct electricity without being dissolved in water. Now, if I test this conductivity meter on a penny, you should get both lights lighting up. And they do. You get both lights lighting up, green and red. So it's a great conductor of electricity in the solid state due to those delocalized system of electrons. Sugar, dissolved in water, would not conduct electricity. Dissolved in deionized water, they'd have to use. And salt would conduct electricity when dissolved in water, but not in its solid state. So based on only the property of conductivity, students should be able to distinguish between covalent, ionic, and metallic substances of unknown identity. And based on the concept of conductivity, they could argue based on evidence how they came up with the answers they did.